This video is about basic indefinite and definite integrals. We've already discussed definite integrals, but this is going to put them in a broader context here. We're going to recall, to begin our notes, the antiderivative introduction. So we've already discussed what an antiderivative is, and we've worked with many examples of them. We're going to add a definition and say this: based on all we learned from the fundamental theorem of calculus, which is in previous videos, we can use the following notation for antiderivatives, also known as indefinite integrals. So we just saw the fundamental theorem as it applies to definite integrals, and based on what that theorem in both of its parts teaches us about the relationship between a derivative and an antiderivative and the integral, in that case definite integral, we can call an indefinite integral basically what we were just seeing, but with no bounds. So notice there's no a and b written with this integral symbol, but we have the integral of f of x dx equal to capital F of x, where capital F prime of x equals f of x, lowercase f of x. You'll recall in the context of doing these antiderivatives, this is where we usually will end up putting a plus c for this arbitrary constant. And so you'll see us doing that in these examples. Now let's see and memorize the table of indefinite integrals in the textbook. Note that we probably know most of these already because they're just antiderivatives, and we've already discussed them that way. Let's try some examples where we want to find the general indefinite integral. Our first example reads, the integral of x squared plus 1 plus 1 over x squared plus 1, and that's dx. Notice there are no bounds given for this integral, so that makes it an indefinite integral, in which case all we're really trying to do is find the antiderivative of the integrand. And so we'll use what we already know with this and call this first term x cubed over 3 plus second term will be just x, and the last term, this would be arctan, or you could say tangent inverse of x. And then if we want the general indefinite integral, we should call this or put a plus c at the end to make that the general arbitrary constant, as we've been used to doing in the antiderivatives. Our second example reads the integral of sine of 2x over sine of x, and then dx at the end. Now, you'll recall there are some trig identities lurking here. We could rewrite this as the integral of, instead of sine of 2x, you may recall that's the same thing as 2 sine of x cosine of x. And then we'll keep the sine of x down below with our dx at the end, but simply rewriting sine of 2x as 2 sine x cosine x hopefully makes it clear that now we could cancel the sine of x's as matching factors, which means we really have the integral of 2 cosine of x dx. And for this, remember, you could even write the constant of 2 out in front, making this 2 times the integral of cosine of x dx, which really represents just the antiderivative of cosine, which would be sine. So really this is just 2 sine of x, and since we want the most general one, we'll put our plus c for the arbitrary constant at the end. Let's try some more examples, but this time we're going to evaluate the definite integral, just as some more practice with these. We've already been doing them. And the first example is the definite integral from 1 to 4 of the following function. The numerator of it is the square root of y minus y, and then the denominator is just y squared. Recall that for definite integrals, we want to use the fundamental theorem. That still requires us to do some antiderivatives, and so we'll rewrite this as the definite integral from 1 to 4 of, and then we could split up this fraction to get the square root of y over y squared minus y over y squared dy, and then we'll just keep this going as the integral from 1 to 4 of, if I combine the powers of y in this first term, I'll end up with y to the negative 3 halves minus, and then 1 over y, if I simplify that second term, all dy. Now, as we just discussed with the fundamental theorem, this can be done using the antiderivatives of these terms. So for the first term, if I add 1 to it and then divide by that new power, we should end up with y to the negative 1/2 over negative 1/2 minus. For the second term, you may recall that this is actually one of our famous function antiderivatives here. This would be just minus the natural log of the absolute value of y. That's in one of our lists of antiderivatives we've already discussed. And we want this evaluated from 1 to 4 as these bounds had set here originally. So we'll go ahead and plug all this in. We could rewrite this just to make it a little more friendly as negative 2 over the square root of y minus the natural log of absolute value of y. And of course this is from 1 to 4. So plugging in the upper bound first, that is 4, would mean we really have negative 2 over square root of 4 minus the natural log of the absolute value of 4. So that's like f of b, capital F of b, plugging in the upper bound. Now we subtract capital F of a, or in other words, plugging in the lower bound, which would be a negative 2 over the square root of 1 minus the natural log of 1. So if we combine like terms and simplify some of them in the process, we'll end up with 1 minus the natural log of 4. I know the 4 was an absolute value, but the absolute value of 4 is just 4, so we wouldn't need to write the absolute value for our answer. Let's try another example. This one is the definite integral from 0 to 1 of 5x minus 5 to the x power dx. So we'll go ahead and apply our fundamental theorem, which utilizes antiderivatives. And the antiderivative of the first term, 5x, would end up being 5x squared over 2, as we understand by now, minus, and then the antiderivative of the second term, which is an exponential, 5 to the x, would end up being 5 to the x over the natural log of 5. So we've worked with that kind of antiderivative already. If it's rusty, practice those formulas. You'll want to get those comfortable and memorized. And of course, this is a definite integral, so we're evaluating this from 0 to 1 as specified. So we could first plug in the upper bound, which would give us 5/2 minus 5 over the natural log of 5. That's like capital F of b, the upper bound. Then we subtract capital F of a, which is plug in the lower bound, which would give us 0 minus 1 over the natural log of 5. And again, we could combine some terms, simplify as much as possible, and maybe end up with something like 5/2 minus 4 over the natural log of 5 for our final answer. Remember, we do not put the plus c with a definite integral, and that can be easy to mix up when you're going back and forth between definite and indefinite. We just reviewed a few minutes back here, or above, the indefinite integral, which does not have the bounds, but does have the plus c. With the definite integral, it does have the bounds, but does not have the plus c. So just practice, 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 and eventually I think you'll be pretty confident with them. Let's try another example. This one is the definite integral from 0 to pi over 3 of the following function. The numerator is sine of theta plus sine of theta times tangent squared of theta. The denominator is secant squared of theta, and this is all d theta. Now, you'll start hopefully rummaging through your list of trigonometric derivatives and antiderivatives to see how we may be able to go about this. Recall that with a definite integral, we're going to use the fundamental theorem, which really turns this into some antiderivatives. But let's go ahead and do a little work on this function so that it looks more usable than the way it's given. So we'll go from 0 to pi over 3. But notice in the numerator that there's a common factor. Sometimes it's assigned to maybe try to factor that out. So let's try to write that as sine theta times 1 plus tangent squared theta, and that's all over secant squared theta d theta. So we just factored out a sine theta from the numerator. But the reason this may be useful is because you may or hopefully recognize a trig identity lurking here. Inside the parentheses of the numerator now, once factored, you can see this 1 plus tangent squared. You may recognize that as, well, secant squared. So we can rewrite this as sine theta times secant squared theta all over secant squared theta d theta. And by now, I'm sure you can see where this is going. These secant squareds will cancel, which means we really just have the integral from 0 to pi over 3 of sine theta d theta, which we can evaluate using our fundamental theorem. The antiderivative of sine will be negative cosine. Be careful on the SIGN signs of those functions. We would want that evaluated from 0 to pi over 3, which means we really have negative 1/2 minus negative 1, which is really just a positive 1/2. Let's try a fourth example. This one is the definite integral from 0 to 2 of the absolute value of 2x minus 1 dx. Now, let's recall, we have to be careful with an absolute value function like this. Let's recall that the absolute value of 2x minus 1 could be defined as a piecewise, where the first piece is just 2x minus 1, but that's if 2x minus 1 is greater than or equal to 0. The second piece would be the opposite of that, so negative 2x plus 1, and that is if 2x minus 1 is less than 0. Now, relevant to this problem, we want to look a little more closely at these boundaries and actually solve them for x in this piecewise here. So when we say 2x minus 1 is greater than or equal to 0, which is the boundary or the restriction on this first piece, if we solve our boundaries for x, which will be more convenient, we can say that the first piece is where x is greater than or equal to 1/2. The second piece is where x is less than 1/2. Again, that's just solving those original boundaries we wrote there for the piecewise pieces, but for x alone instead. Notice that we're trying to evaluate this integral ultimately from 0 to 2 as given these original boundaries, but the boundary of the piecewise definition has this important value of 1/2, where the function looks different depending on which side of 1/2 you're on. So we're going to have to split up this original integral into a couple pieces. First, we'll go from 0 to 1/2, since that's the first segment, yet considering the boundary of the piecewise. And in that piece, we're using the negative 2x plus 1 dx. Okay, so that's again this second piece where x is less than 1/2. But that's only part of our interval, so we're going to then add on to that the rest of it, which would be from 1/2 to 2, finishing out the desired bounds here. But of course, that's the other piece, which means our function is 2x minus 1 dx in that interval. Now, we've been calculating a lot of these integrals by hand, one little painful step at a time. They're not terrible, but it's often a lot of arithmetic. And in some examples, I've kind of mentioned that you can use a calculator to speed some of that up, and I've done so with the arithmetic there. In this example, I'd like to go even further and show you that a TI-84 Plus calculator, as we're used to using, can not only do the arithmetic, but can even handle an input integral just like this. If we turn on our TI-84 Plus calculator and then go to the math option, you'll notice if you go down the list far enough, it's often the 9th option in the list, and that says fnint, and it's a function pre-programmed into this calculator. We're going to utilize that. If I hit enter, you'll notice in the screen shows up pretty much the syntax we're used to of a definite integral. So we could utilize this to calculate these integrals a little quicker. Again, we've shown all of our work so far, which is always important, but now we're just going to demonstrate how to handle these calculations with a calculator. So the first integral we had bounds from 0 to 1/2, so we'll go ahead and just put those in. Of course, with a nice decimal or a nice fraction like 1/2, you could put just 0.5, that'd be fine too. That first function was the negative 2x plus 1, and then you always have to put your variable of integration in here, which of course we're just using x for. We'll keep the same button there. So that's really our first term in this split integral we've now been using. If I hit enter, it'll calculate the value for me, and it turns out this integral is equal to 0.25, which of course is just 1/4. Using the exact same feature on the calculator for this second integral, this second term here, we would get in that case 9/4 for that value. And so of course putting those together will give us 10/4, which can reduce to 5/2. And so now we have our exact answer with a little help from the calculator on those. But notice we showed a lot of work in the process. It's always important and necessary to do that. Let's try another example. This one is the definite integral from 0 to 3 pi over 2 of the absolute value of sine of x. Now we just discussed just did an example using an absolute value function, and so we're going to kind of use the same idea on this one. The absolute value of sine of x could be defined as a piecewise, where it's either equal to sine of x or negative sine of x. Okay, so it's equal to itself, sine of x, when sine of x is greater than or equal to 0. That's consistent with absolute value definitions in piecewise form. Or it's equal to its opposite when the sine of x is less than 0. Now let's recall or review a couple things about our sine function. So if we take a look at a sine function, and really we're only ultimately talking about between 0 and 3 pi over 2. And let's recall a sine function is periodic, and of course it intersects at the origin, and then it would go through one full period by the time it gets to 2 pi, and it would hit another x-intercept in the middle at pi. So as is familiar, the function has a snake-like shape, so it goes up through quadrant 1, down back through pi as an x-intercept, dips down and then heads up back up, hitting the x-axis again at 2 pi. Now, if we're only going from 0 to 3 pi over 2, let's understand what that means for this function. If I were to mark off 3 pi over 2, of course, it would be between pi and 2 pi. So we're really only looking from 0 to 3 pi over 2 ultimately for this whole integral. But notice that the sine function is both positive and negative in that space. So if we go back to where we've defined this piecewise, one of our pieces was defined for where sine of x is greater than or equal to 0. Well, according to what we just looked at, that's the same thing as saying that x is between 0 and pi. Okay, and then secondly, where is sine of x negative? Well, that would be where x is greater than pi, but less than 2 pi. And so really we're only talking about those places. And so we're going to have to split this integral up, but using these boundaries appropriately. We'll start by going from 0 to pi. Remember, pi is kind of where the boundary occurs of sine being either positive or negative here. So we want, first of all, just 0 to pi, and in that case we would use sine of x dx as our function. That's the first piece. Plus, we have to tack on the rest of it, which would go from pi to 3 pi over 2, finishing out the rest of our given interval, or the given bounds. And in that case, we would use negative sine of x dx. So now we go ahead and apply with our antiderivatives to get negative cosine of x, evaluated from 0 to pi, plus cosine of x, evaluated from pi to 3 pi over 2. So we're just using antiderivatives and keeping our bounds as discussed. Of course, when plugged in, this will turn into 1 minus negative 1 plus 0 minus negative 1, which ultimately will give us a value of 3 for our answer.